Okay, so it's my pleasure to welcome you to the 32nd International Conference on Formal Power Series and Algebraic Combinatorics. My name is Matjaž Konvalinka. Today we will have 3 speakers. Each talk is 25 minutes long with 5 minutes in between for questions and a short break. The chat monitor for today is Dan Beta. So, now it's my pleasure to introduce our first speaker. That's Liam Solus from the KTH Royal Institute of Technology in Sweden, and he'll be speaking on some algebraic properties of lecture hall polytopes. Go ahead, Liam.
Okay, yeah, first, so let me say thank you to all of you for joining the meeting today. And I also wanted to start by giving a special thanks to the organizers of FPSAC 2020 online. So this is actually my first FPSAC that I've ever participated in, and I was really excited about it. So I'm glad that we were able to still have the meeting in some form. So this is really nice. So thank you for that. So today I'll be talking about the contents of the paper that I submitted to FPSAC with Peter Brandon, who's also at KTH. And this will focus on some of the algebraic properties of lecture hall polytopes. So these are the main combinatorial objects of interest in this talk, are these lecture hall polytopes. And sort of, I guess I can say, like, classically, this term referred to a certain family of simplices, which are perhaps now better referred to as S-lecture hall simplices. So how do we construct these objects? Well, we start with a sequence of positive integers, say S1 up through Sn. And we can think about starting with a little unimodular simplex like this one here. And the idea is that what we're going to do is stretch this simplex in direction I by Si. So for example, if our sequence is 2, 3, then we'll stretch it by 2 in the first direction and 3 in the second direction. So more formally, this object is just all points in n-dimensional real Euclidean space lambda, satisfying the sequence of inequalities here. So these objects have been studied for their lattice point combinatorics, but they're actually a truncation of the original object of interest, which was the so-called lecture hall cone, which is produced by dropping this less than or equal to 1 term here. So the lattice points in the lecture hall cone are referred to as lecture hall partitions. And these were enumerated for, like, the first sort of, the seminal paper on this topic was considering the sequence 1, 2, 3 up through n, and the lecture hall partitions in that cone. And these were just the lattice points in that cone. And these were enumerated by Bosquet-Moreau and Ericsson in their 1997 paper, where they got out some very beautiful formula that mirrors that of some classic results of Euler. So their initial work actually inspired, let's say, like 25 years now worth of research on lecture hall partitions and their associated geometric objects and lattice point enumeration questions. A lot of this work is nicely summarized it was driven in large part by Carla Savage, and she wrote a very nice summary of this which was published in 2016, called The Mathematics of Lecture Hall Partitions. So if you're interested in learning more about these things, I highly encourage you to look into this. But our main object related to this story today will be these lecture hall polytopes, some of which will be these S-lecture hall simplices. So these were introduced in 2012 by Savage and Schuster to further this story on the enumerative properties of the lattice point combinatorics of lecture hall partitions by way of Ehrhart theory. So the idea here is so how do we think about lattice point enumeration from Ehrhart theory perspective? Well, this was introduced to us in at least Marielle's talk on Monday. The idea is we start with a convex lattice polytope P, and we're interested in enumerating the lattice points in its dilates, all positive integer dilates. So we're interested in this generating function here, where the coefficient of x to the k is the number of lattice points in the kth dilate. So when written in a closed rational form, this actually has a really nice form, the numerator polynomial here is something known as the H star polynomial of P, which is really just the same as what is actually a polynomial over here. This lattice point enumerator is actually a polynomial. This is the same up to a change of basis. And the nice thing about this basis is that it's encoding all of this lattice point enumeration properties using only non-negative integer coefficients. So this polynomial has only non-negative integer coefficients, which makes it very nice to try and understand from a combinatorial perspective. So naturally, we ask a lot of enumerative questions about this, and in particular, what sort of inequalities might hold amongst its coefficients. So for example, typical questions are like, given a family of polytopes, when is this polynomial going to be unimodal, log concave, real rooted, and so on and so forth. This, of course, has been studied for these S-lecture simplices. So Savage and Vasanti in 2015 showed that these H-star polynomials are always real rooted, which by some classic results implies that they're log concave and unimodal. While real rootedness has been, well, in recent years, we've been able to show that lots of interesting families of polytopes have this real rooted H-star polynomial, but many interesting families also don't. So historically, we've used a lot of other different techniques other than proving real rootedness to identify when these H-star polynomials are unimodal. And a lot of them rely more directly on the geometry of the polytope. So what is actually happening geometrically with this polytope, and how can we see the unimodality more directly from there? So what are these? So one sort of natural question here is, even though we have this nice real rootedness result, can we, in certain cases, rediscover this unimodality by these more direct geometric means? So what are these geometric approaches that we might take? Well, they typically rely on having a nice lattice triangulation of the polytope. So what do I mean here? I mean a subdivision of our polytope into a simplicial complex where the zero-dimensional cells all live in the lattice of interest here. So in this case, our lattice is z to the n. Which are the nice lattice triangulations for trying to detect things like unimodality of H-star polynomials? Well, it turns out that the nice ones are things like unimodular triangulations. So these are triangulations where the facets have smallest possible volume. So because our zero-dimensional cells have to lie in the lattice, this is some sort of well-defined term here. So in this case, in the standard z to the n lattice, we want them to have volume 1 over n factorial. Another nice property of triangulations is when they are regular. So this means that we want it to be realizable as the complex of lower faces of some lifting of P. So in particular, we're going to embed our polytope into n+1 dimensional space. And then we're going to imagine that we lift our lattice points in it up into this new dimension. And then we're going to take the convex hull of that. And when we look at it from below, we're going to project the faces we see back down onto our polytope to get a subdivision. If our lifting function was significantly generic, then this will give us a triangulation. So it turns out that if we have these regular unimodular triangulations in certain nice cases of polytopes, they can be used to identify when the H-star polynomial is unimodal. Their existence can imply that. So then the question becomes, is given a polytope, how can we go about identifying such regular unimodular triangulations? And it turns out that this can be done via algebraic methods and analyzing certain algebraic objects associated to the polytope if this polytope is what we call IDP. So this is short for the integer decomposition property, or sometimes called integral closure of the polytope. And it essentially says that for every positive integer k and every lattice point in the kth dilate of the polytope, there should exist k points in the original polytope, again lattice points, that sum up to give us our point, okay? So it turns out that if we have this property, then sort of certain algebraic objects, one which is closely associated to the H-star polynomial, and another which is closely associated to regular unimodular triangulations, come together in a nice way. So what are these algebraic objects? The first one is called the toric ideal of our polytope. So how do we construct that? Well, we start by taking our polytope P and living in some n-dimensional space and some algebraically closed field. We're then going to embed our polytope at height 1 in n+1 dimensional space and just index its lattice points as a1 up through an. We're then going to consider a polynomial ring with coefficients in k, where we have one indeterminate for every one of our lattice points. And we're going to map that ring into a polynomial ring where we have plus or Laurent polynomial ring, where we have plus or minus one determinant, indeterminate for every dimension in our n+1 dimensional space. And the idea is that we'll map xi, the indeterminate associated to ai, to t to the ai, where our lattice points appearing in the exponent vector here. The kernel of this map is going to be our toric ideal. And it turns out that if we have certain nice bases of this, known as reduced Gröbner bases with what we call square-free initial ideals, will index, well, they'll essentially correspond to regular unimodular triangulations of our polytope considered in the lattice generated by these lattice points in our polytope. So this object associates naturally to regular unimodular triangulations, where on the other hand, we can construct one that naturally attaches to the H star polynomial. So here we start by, for every positive integer, we're going to construct a vector space where we have the span over a family of Laurent monomials, one Laurent monomial for every lattice point in the kth dilate of our polytope. So in particular, if like the first n terms of this are used to encode the lattice point and its coordinates, and the last term is used to encode which dilate it lives in. So by taking the direct sum of these, we produce the Ehrhart ring. And naturally, if just thinking about the previous definition of our H star polynomial, we see that the numerator of the Hilbert series of this ring is that H star polynomial. So how does everything relate? Well, it turns out that when our polytope is IDP, this Ehrhart ring is the coordinate ring of this toric ideal here. And at the same time, the lattice generated by these points is this lattice z to the n, which was where we wanted to consider our original unimodular triangulations. So everything sort of comes together nicely when the polytope is IDP. And the idea then is that we want to use we can identify a Gröbner basis with nice properties for this ideal here to deduce nice things about this H star polynomial here by way of these regular unimodular triangulations. So what is our goal? Our goal is to see that our lecture hall polytopes are IDP, and also that we see if we can identify some Gröbner bases for this ideal, and think about this as a new perspective, more geometric on unimodality of this polynomial. But we don't have to work just in the case of these S lecture hall simplices. We can work for part of the story more generally in a larger class of lecture hall polytopes. So these are known as our S lecture hall polytopes, S lecture hall order polytopes. And these, just like how our S lecture hall simplices were sort of a stretching of a unimodular simplex, we can think about a S lecture hall order polytope as a stretching of a classic order polytope. So what do we do here? We take a naturally labeled poset P, such as the one depicted here, and we take again a sequence of positive integers. So maybe 2, 4, 3. So 2 goes with 1, 4 goes with 2, and 3 goes with 3. So our lecture hall order polytope is defined by this collection of inequalities here. So the ith coordinate is bounded between 0 and Si. And whenever we have a order relation in our polytope, I less than j, in our poset, I less than j, then we should have the inequality lambda I over Si is less than or equal to lambda j over Sj. So similar to what we saw for our simplex. So, well, if S is the sequence of all ones, this is just the classic order polytope depicted here for our little poset. And we see then if we consider this sequence 2, 4, 3, well, we're going to stretch this polytope by 2 in direction 1, 4 in direction 2, and 3 in direction 3. Okay. So this is a recent generalization of these S lecture hall simplices, but people have already become interested in their geometric, enumerative, and algebraic properties and ask questions about them similar to the S-lecture-Hall simplices. So in particular, here is just a subset of some of the open questions that exist around these families of polytopes right now. Of course, don't expect you to digest the slide in its entirety right away, but I just wanted to put it here so that you can come back and think about it, because I really encourage you to, there's a lot of interesting combinatorics here and open questions, and there's a lot of combinatorialists in this audience here, so I hope you guys come back and try your hand at some of these questions. So the only question here that will settle in its entirety today is the first one, which is a conjecture of Hibi, Olsen, and Tsuchiya from 2016, which claims that for any S-lecture-Hall simplex, the polytope will be IDP. Similar, following the story that we just went through, they also conjectured that any S-lecture-Hall simplex should admit a unimodular triangulation. And this fourth conjecture listed here, Brendan and Leander, in their paper in which they introduced these S-lecture-Hall order polytopes, conjectured that another family of these S-lecture-Hall order polytopes has a regular unimodular triangulation. I also, just to show you some of the extent of the open questions here, there's also questions that open questions that pertain to whether or not these H star polynomials are, for example, gamma positive, and also if we can gain some combinatorial interpretation of things like their gamma coefficients for their H star polynomials in the symmetric case, or local gamma coefficients and things like this. So there's a lot of interesting stuff to be done here, and today we'll give some partial answers to these conjectures. So the first one is about this IDP question. And it turns out that we can, the conjecture of Hibi, Olsen, and Tsuchiya holds not only for S-lecture-Hall simplices, but more generally for any S-lecture-Hall order polytope. So any S-lecture-Hall order polytope will be IDP. And the proof is relatively straightforward. I mean, the idea is that if you start with some lattice point living in the kth dilate of this order polytope, and you think about that lattice point and the sequence Sn as points in Zn with the usual product order on them, then you can consider their join there. And this, you can check, will be a point living in the original order polytope, a lattice point. And if you subtract this off, well, then you'll end up with the remainder being something that lives in the k minus first dilate. So again, a lattice point. So working our way backwards iteratively, we get k lattice points that sum up to lambda. It's the basic principle of it. So, but the good news now is that since all of these polytopes are IDP, that whole algebraic, geometric, and then combinatorial story that we just went through works in this case. So we can identify reduced Gröbner bases for this toric ideal, IOPS, with something called a square-free initial ideal, in order to identify a regular unimodular triangulation of OPS, of our order S-lecture-Hall order polytope in the lattice Z to the N. So this is what we want to do. I mean, unfortunately, we can't do it yet for all of these S-lecture-Hall order polytopes pertaining to these conjectures, but we will be able to do it for a family that touches on the previous conjectures here. But first, for those of you who aren't so familiar with these concepts, what is this Gröbner basis that I'm talking about, and what are these, and how does it relate to these regular unimodular triangulations? Well, the idea is, again, that we start with our lattice polytope P, and we can again index its lattice points embedded at height 1 as A1 up through AM. And we're going to work in a polynomial ring where we have, again, one indeterminate for every one of our lattice points. But now we're also going to consider a term order, denoted by this little squiggle here, on our monomials in this ring. And you can think of this as just being a fancy, a total order of our monomials with some nice additional properties. So under this term order, we're going to have that for any polynomial f, okay. Oh, there we go. Yeah, for any polynomial f, we're going to have an initial term. So this is just the largest term with respect to the given term order that we've taken. And then for any ideal, we can define its initial ideal to be the ideal generated by those initial terms for every polynomial in our ideal. So a Gröbner basis, or a reduced Gröbner basis for this ideal I with respect to our given term order is just a basis for the ideal that plays nicely with this initial ideal. In particular, it's a finite collection of polynomials whose initial terms under the given term order is the unique minimal generating set for the initial ideal. So we also generate the initial ideal. And on top of that, we want, it's reduced in the sense that no non-initial term of any one of these GIs in our generating set here is divisible by some element in this unique minimal generating set. So that's the basic idea. If you're familiar with this, this is very old hat. And if you're new to this, then hopefully then you at least have some sense of the words that are floating around here now. So it turns out that if you can identify one of these reduced Gröbner bases for this toric ideal with such a square-free initial ideal, meaning there's no squares in these initial terms here, then we've actually identified a regular unimodular triangulation of P. So in our case, we can do this for a family of these S-lecture HallPolytopes, in particular, those S-lecture Hall simplices, where the sequence S1 up through Sn is a sequence whose first order difference sequence is 0, 1. So what does this mean? It just means that the sequence is weakly increasing, and every time it is strictly increasing, it increases by at most 1. So to identify our Gröbner basis, we need to, we end up not working directly with the S-lecture Hall simplex as we defined it, but a slightly transformed version of it with the same lattice point combinatorics. In particular, we apply this unimodular transformation here, and then a homogenizing transformation that embeds our polytope into the plane where the sum of all the coordinates is Sn plus 1. So if we do that, what we get out is a polytope, which we denote by ANS, which is defined by this collection of inequalities here. So the first two lines of inequalities here show us that our polytope is a subpolytope of some what we call alcoved polytope, which is nice because alcoved polytopes are known to have nice regular unimodular triangulations. But then we also have these additional inequalities here. So here we see where this property of the 0, 1 first order difference sequence comes into play. So we have this Si plus 1 minus Si here. And essentially these inequalities become trivial when there's no, when we don't increase, but when we do increase, this becomes a 1, and we have to consider what's happening here. So most of the technical details of messing around in this project were sorting out how to understand what's happening with this family of inequalities. So, right, so what are we doing? We now have the lattice points in this polytope, and we're going to consider a polynomial ring where we have one indeterminate for every one of these lattice points. And we want a term order on the monomials in this. So a total ordering on these monomials, which means that essentially we're considering multisets of these monomials. And or multisets of these lattice points. And as it turns out, our ordering on these monomials is just going to be a purely lexicographic one. The way that we do this is we impose a lexicographic ordering on the points in the polytope, and then we extend this to the Cartesian product of k sets of these lattice points, which we index with associated multisets. To give us a total order on the k collections of k lattice points within this polytope. So what are we doing here? We're essentially saying that we can impose a lexicographic order on collections of k multisets, and when we consider a collection of k multisets associated to lattice points in this polytope, which we call these S-lecture Hall multisets, then under this lexicographic order, we can find a lexicographically minimal set of K multisets that are also these S-lecture Hall multisets, indexing points in this polytope, that have the same multi-union. And this set, these minimal sets will be exactly what we use to define our Gröbner basis. So what's the final result? The idea is that our Gröbner basis for these S-lecture Hall simplices for this 0-1 sequence is given by this marked set of quadratic binomials here, where we have a pair ij of S-lecture Hall multisets, and we're subtracting off the indeterminates associated to their lexicographically minimal pair that has the same multi-union. So this turns out to be a reduced Gröbner basis for this toric ideal ANS, which in turn gives us a regular unimodular triangulation of this polytope, which is then up to unimodular transformation, a regular unimodular triangulation of the original S-lecture Hall simplex. So yeah, so that's the main contents of the paper that we submitted. The nice take-home message is that all of these order polytopes are IDP, which means that we should be searching for more of these regular unimodular triangulations to see if we can think about reproving some of these unimodality results from this more geometric perspective. Potential directions for future work include things like extending these results to non-simplex S-lecture Hall order polytopes, or working with not weakly increasing sequences. Be very interesting to see results in any of these directions. So I again encourage people to try their hands at some of these problems. So thank you very much.
Thank you very much. Liam, can you unshare your slide? And now I'm going to give the word to Dan Beta for questions.
Hi, Liam. Thank you, Matias. There are a couple of questions in the chat. So Sergi Elizalde, actually, do you mind unmuting yourself, Sergi, to ask the question? I can ask it for you, but it's...
Sure.
Find it better if
Yeah, no problem. So I was wondering if the conjectures that you mentioned become any easier when S is just the sequence 1, 2, 3 up to N, which was the original definition of like lecture hall partitions.
Well, yeah, so I think this was originally what people were trying to do, was to triangulate this polytope nicely. So this one falls, via our methods, we get this, right? So this is one of our examples. So so yes, I think they become easier. So I don't know. But yeah, I don't know. I mean, gamma positive. So this thing, the gamma positivity questions are sort of clear for this one. Because this has, I didn't talk about its H-star polynomial, but the H-star polynomials of these S-lecture Hall simplices are the S-Eulerian polynomials, which generalize the Eulerian polynomial, and the Eulerian polynomial is the H-star polynomial for exactly this sequence. So all the nice enumerative properties that we like happen here. So.
There is a second question from Jiayuan Wang, and I'll ask it because he has no microphone. So for a polytope with no IDP, does it have interesting properties such as regular unimodular triangulations?
Well, if you have a regular unimodular triangulation, this turns out to imply that you're IDP. So, but there are still interesting things that you can do here, even if you can't identify that your polytope has IDP or that you have a nice regular unimodular triangulation. For example, in a recent paper with one of my master's students, Niels Gustafsson, we actually showed that the entire family of S-lecture Hall order polytopes are what we call box unimodal. So this means that essentially they have a triangulation actually into S-lecture Hall simplices that have all unimodal local H-star polynomials. And in the case that the H-star polynomial of the whole polytope is degree D and symmetric with respect to that degree, then this property in turn implies unimodality of the whole H star polynomial. So if we knew that even before we knew IDP. So I mean, yes, there's definitely interesting properties to be studied even when you don't have this. So.
Okay, thank you. Those are all the questions from the chat, and we're up on time as well. So I propose we go back to our second speaker, Matthias.
Thank you very much. So let's thank Leon again.